Okay, today we're going to look at the bond graphs versus block diagrams using a mechanical element, an I element. And so let's begin by setting up both columns here. Here we're going to put the block diagrams on the left hand side. Okay, so block diagrams, and we're going to put the bond graphs on this side. Okay, bond graphs like that. Okay, so let's just propose a simple example that we need to use so that we can illustrate this principle. So let's just draw it over here, and let's just write the equations of this example of this system. We have a force applied over here like that. Let's call it F, and it's going to, as the force is applied, is going to acquire a velocity like that. For this kind of situation, what we usually know is we apply Newton's law. So let's just write down now Newton's law. And what is that says? What does Newton's law say? Newton's law says that you're gonna say in here that the force F is equal to mass times the acceleration, or you can write it like this: m times d of x dot dt, like this. Or you could also write, as we know, m times d squared x dt squared. These are the several ways of writing Newton's equation for this kind of situation. What I think we need to first notice is that if we if we have this differential equation that represents the motion of this, we need to recognize that there is an input and there is an output. So in here, for example, this on this side, this would be the output, and this on this side, you will have the input over here. You could also call it this side, you could call it the action, and this side you would call it the reaction. Or you could call it the cause here, and this would be the effect. So if you write a block diagram of the system here, you would do something like this. You would say we have an input in here that comes in, which is this x dot, and then we have this action that we take on the signal here is going to get differentiated, and so in here we have the new signal is d of x dot dt, like this. Yeah, and after this we multiply by this m, or in here, and the result of this is going to be this force. So what we have done is written we have drawn actually a block diagram of the differential equation. That's basically what has happened here. We have this equation up here, and then we have this up here we have this equation, and we have the corresponding block diagram in here. So we could perhaps continue putting some of those labels that we're using to help ourselves. This in this case is going to be the input here, and then this is going to be the output over here. Okay, so we can also write the law a little differently. So we could say, let's just write that here. We say, let's write the law. You could say, I would say, why don't we go here? But we can also write in another form. Instead of writing F equals ma, let me just put this equation in front over here, and then we'll see in here if we write it like okay, let me start with what I have. Okay, this is m times d of x dot dt, like this. Let's say we take the we integrate both sides. So you have f dt is equal to m times x dot in this case. Yeah, and I could write this like this. I could say that x dot is equal to 1 over m times the integral of f dt. Yeah, so it's very obvious that what we have, what I had up here is what I had on this side over here is the derivative form, and what I have on the bottom is the integral form. So I am going to write it down. This is going to be my derivative form. Okay, so as we know, the block diagrams that we see in here are a representation of the equation. So this equation that is in derivative form is actually represented over here. But as I mentioned a moment ago, we are going to rewrite the equation in a little different form. So in this case, if you do that, what is going to happen is that you have on this side, this is going to be your input here. Now this is going to be your output on this side. So how would the block diagram look like for this one? This is going to look something like, in here you have the input, which is going to be this f, and then you come and do the integration here. 1 over s for integration. So what do we have right now? This is going to be f is equal to, no, f, what am I saying? F dt is what we have here. And now on this side, if we multiply it by 1 over m, then we are going to have the output over here, which is x dot. See? So in this integral form, we have the result is the velocity is 1 over m times the integral of f dt. So we need to see that to be able to compare with the bond graph models. So we have the derivative form up here, and on the bottom we have the integral form. Let's write it down so that we can have a nice reference here. This is okay. We have here, this is going to be my integral form. Okay. One thing that we should add to both of this is the concept of the variable p, the momentum here. The momentum is really m times dx dt here. Yeah. But if you differentiate this and you differentiate the momentum u versus dp dt, you have that this is m times dx squared x dt squared. So this is in fact is f. So the you have that the momentum in this case dp dt, the derivative of the momentum is equal to mass times the derivative of the velocity, because that's what Newton's law says, is that the rate of the summation of forces equals to the rate of change of momentum. And we can write also over here, down here, maybe we'll switch colors now, and we say okay, this is, in here we put that p again. The concept of p is m times dx dt, right? But from up we have learned that dp dt is equal to f, and based on what we have in here, you know, we can put it in this form. But on this side here we have that dp dt is f, and that you have that x dot is equal to 1 over m the integral of f dt. And this set of equations that you see here, these are the equations of the integral form. So that's this one here, the integral form, and this equation here is the one of the derivative form. So okay, now let's take a look at the bond graph model on the right hand side, some representation that we want using bond graphs in here. And how do we represent in this case in the same thing using bond graphs? We use the symbols like C or I. In this particular case we have an I element, so let me just correct this in here, and then we're gonna say this is my I element like this. Let's say just an I element over here, and then we need to we represent it with a little symbol that is composed with two parts. In this case there is a line and a crossbar like that. Yeah, think of this as if you were holding here. Let's see, there's your hand right there, and you are armed with this object in here to put an effort and press it to somebody. You would move it to the right like that, and you will put this, we will call this the output in here, and this is going to be the input over here. So this is, I am just making this little example with your hand just so that you can see it. Just imagine holding it in there, and if you push it to the right, then obviously something comes out of the I element into the rest of the connections here on the element. So this in here means that this is your F, the output, and this is the input, which is X dot. So if this is true, F in this case is equal to M times dx dt is like this. And so this obviously is the derivative form when you have it this way. This is your derivative form in here. Okay, and in here you will write that P is equal to M times dx dt. So dp dt is really F, yeah. But if that's the case, you also can write that dp dt is like this: dp dt is equal to M times d of X dot dt, like that. And these two represent the equations of this I element in that we see up here. Equations of this I element are these, and they are in derivative form. So these equations that you see on the right hand side here, this is what makes this whole thing equivalent, like this. So these are equivalent. This language, this example that you see here, would be understood by Simulink. Alright, this block diagram like that. And then let's just put it, that would be the way Simulink will read this example. And the one on this right hand side, the symbol as you see here, would be understood by the other software, which is called CAMG, which stands for Computer Aided Modeling Program with Graphical Interface. So if we go down a little bit and we look at the other form in here for the bone graft model in here, and if we look at this other form, let's see, we have the I element over here like this, and we're going to use the same type of representation here. Oh, we need to change the pin, and that is, you see, in this case it's very obvious that you could see that the output is the velocity, see, and the input is this force. So the force is represented by that crossbar. So what I'm going to do is I am going to put the crossbar like this, yeah. And just imagine, like I said, this is just an imagination, as if you were holding it with your hand. So I'm gonna draw your hand right there, Okay, there you go. You're holding it. Just imagine right now holding that, and then you're gonna push it towards the crossbar. So this would be as if you were pushing it this way. That means that the input to this I element is this force F, represented by the crossbar, but the output of F is represented by this line, which in this case is x dot. So when you have the symbol here represented like this, you know that that what you have is an I element in integral form in this case, because if x is the output, you have that x dot is equal to 1 over m times the integral of f dt. We also know that dp dt is equal to f, and these two now become the equations for the integral form of this element in here. Let me just put them here on this like that. So this up here, this is the derivative form, and the one down here is the integral form. So when you have a bone graft model like this, it's totally equivalent to this block diagram here. I'm gonna put here equivalent. This is just like speaking two languages. If you do it in block diagram form, it's gonna be represented like this. If you do it in bone graft form, it would be represented like that. But both of them both of them represent the same equations, and therefore they are two totally equivalent representations. And that's how we can see if we compare the block diagrams and the bone graft models, that although the representation looks here in blocks and here looks in the symbol, the content is exactly the same, and therefore the equivalence between both of these methods. I think what we are going to see is that in this particular case, everything needs to be derived by hand, the equations as well as the block diagrams. But this approach is oriented towards the automation of the modeling process, such a way that if a computer understands the symbols, all the equations would be contained within those symbols, and the computer would actually generate the models for us, so that we can do the computer simulations. So that's the study of the I element, both in bone graft form as well as in block diagram form.